Well, I first sort of got interested in this stuff when I was a research fellow at Cambridge in my second year, I think it was, and and Dennis Sharma, who was a great person who taught me an awful lot of physics. I started off doing pure maths, and he decided I would be somebody who would be worth promoting doing physics. He was quite right. I didn't know much physics, but anyway, he suggested that we might go to a talk at London, King's College London, which was being given by David Finkelstein. And I didn't know much about GR at the time. Dennis and I went to this talk. David Finkelstein was describing, first of all, the well-known Schwarzschild solution, which is a spherical symmetrical solution of the Einstein vacuum equations. And there is a certain limit to how far you can extend it. I mean, the solution sort of goes crazy when you get to a distance of r equals 2m, and in sort of natural units, r being the radius and m being the mass. And when r is twice the mass in these natural units, you find the thing goes wrong. And people were calling it the Schwarzschild singularity. Anyway, so I went to this talk by David Finkelstein, and he described how you could have a coordinate system which got you through. So you could sort of go through it. It's the picture we now have of a black hole, basically, where you have a horizon. It's not a singularity, but you choose your coordinates appropriately, and you can see it's really just a horizon. And you can fall through it, but you can't get out again. It's a one-way, sort of one-way barrier. Anyway, so he described how you can get through and get rid of this singularity. And I remember coming away and thinking that he's got rid of this r equals 2m singularity, but there's still this singularity at 0. And then I wondered, and I thought, well, maybe you can't get rid of that one. I don't quite know why I thought it that way around, but I did. I thought there must be some reason why you can't get rid of that one. I could see why you couldn't in the exact solution, because the curvature goes to infinity. So that's a genuine, what we call a singularity, curvature singularity. The curvature becomes, space-time curvature becomes infinite. So that's a problem. But I wondered whether, if you say perturb this solution, make it more irregular, not exactly spherically symmetrical, but wiggle it around a bit, will you still get that singularity? And so I thought, well, maybe there's a theorem which tells you that you can't get rid of it. I thought that way around. That's what I thought. And I thought, but I haven't never heard of such a theorem, and David didn't mention it. So I wondered whether one could prove such a thing. So I thought, well, what do I know about general relativity? Not much. So I thought, well, I know what I might try. Two-component spinors, because I'd been to these lectures by Dirac, the great quantum physicist Dirac, and he'd taught us about two-component spinors. It was quite interesting because his famous equation is what's called four-component spinors, but you can build them up out of these simpler entities. And I thought they were wonderful. I must say I liked his lectures on that. A lot of people didn't like his lectures because they said it's just like his book. But I hadn't read his book. So I thought his lectures were great. And particularly learning about these two spinors. So I thought, well, why don't I apply these two spinors to general relativity? And the thing sort of worked so beautifully that I got stuck in the subject. Particularly the curvature, the space-time curvature. You see, the curvature splits into two parts. One is the vacuum part, and the other is the matter part. And the matter part is what people usually talk about as the right-hand side of Einstein's equations. But there's the other part, which comes from the gravity itself, which is called the Weyl curvature. And this is complicated in normal descriptions. But when you write it in these two spinors, it comes out beautifully. Completely symmetrical object. And this really started me off on general relativity. Now that's a sort of prelude, because that was about a little bit over 10 years, I think, before I started thinking seriously about how to prove that this singularity in the middle was stable. You couldn't get rid of it by wiggling the solution. And the interest in this came about because of the discovery of quasars. Well, the quasars were very extraordinary things. People seem to think they must be enormously energetic, enormously huge objects, very distant because of the redshift. And people argue whether redshift really was the expansion of the universe or something else. But the general consensus was that it really was. They were really the distance that they seemed to be, and therefore they were that powerful that they seemed to be, and therefore there had to be an awful lot of energy squashed into the size, but they had to be fairly small in the sense of being smaller than the solar system, because the variations in these signals were so rapid that you couldn't have that if they were too big. You know, within days or weeks, you've got the changes in the signals. So they had to be sort of things where you get this collapse situation. Well, this had been studied in this paper by Oppenheimer and Snyder. They studied a dust cloud. What does dust mean? Dust means you have matter which doesn't have any pressure. So it's just dust. It doesn't push itself apart. So it's very special in that respect. Secondly, the solution that they looked at was exactly spherically symmetrical. So it's really the same as the Schwarzschild solution, but written down in a way where you can extend through this horizon and follow the matter into the center. But since it's exactly spherically symmetrical, all the matter falls towards the center, and it's no pressure, so there's nothing really to stop it. And the fact that the density becomes infinite, the curvature becomes infinite at the center, it was well known to people. It was certainly known to me. I think I learned about it from John Wheeler at Princeton, whom I'd worked with for a while. And the Weyl curvature goes to infinity at this point. Everything goes to infinity. It goes crazy. But maybe, of course, if you wriggle it a bit, then you'd get these... I mean, if you're going to have gravitational radiation and all these signals coming from these quasars, it's got to be something irregular. It couldn't be exactly spherically symmetrical, or you wouldn't see anything. If any kind of signal comes out, it's got to be irregular in some way. So clearly, the Oppenheimer-Snyder solution was not typical. And so you might imagine, I think as people normally believed, that as the collapse goes, the complications would get greater and greater, would swish around in a complicated way, and come swirling out again. Now, this view was confirmed, I would say in quotes, by a paper which was written by two Russians, Lifshitz and Khalatnikov. And they had concluded in their paper that in a general case, you would not get singularities. Now, I found this rather puzzling, and I did look at the paper. I didn't see the mistake. There was actually a serious error in the paper. I didn't look at it carefully enough to see the mistake. I just thought the techniques they're using I didn't find very convincing, and that maybe that's not really a very good argument, and we have to think of it in a more serious way. So I started worrying about asymmetrical collapse. And I remember walking through the forest. I used to live near a forest at that time. And I'd walk through the forest and try and imagine what it would be like in this collapsing situation, and everything, curvatures getting bigger and bigger. And I came to the conclusion that it had to be a non-local condition. You couldn't say that the curvature is getting bigger than a certain value is a problem. It's got to be some non-local feature, so it's a global characterization. I didn't know at the time what this global characterization would be, but that was the view I had. It's got to be some global characterization. I had been working on other problems at this time, which led me into thinking in certain kinds of directions, which was useful to me. So I had a feeling for how you could talk about spacetimes in general, not looking at very specific solutions, but looking at them in general, how do light rays behave, how they focus, and that sort of property. It was a general feature. So I had some feeling for that. And I remember not quite knowing how I could characterize that the collapse had gone too far. Sort of, what is the point of no return that would say, and it's got to be, as I say, a non-local condition, not saying that here the curvature's got too big or something like that. It's got to be some characterization of a more global character. I hadn't any idea what it was. But there's a story I often tell about this, which was I was walking to my office in London. I worked at Birkbeck College at the time. I lived out in Stanmore, so I had to take a long trip in on the bus and the tube and then walking. On this occasion, I was walking with Ivor Robinson, who was a very English mathematical physicist, But he was working in Texas. The Americans all loved him because he had this wonderful way with words. He really did. He talked very beautifully in these terms. He never wrote anything. Hardly ever wrote a paper. He always had collaborators to do that. But he had this wonderful way with words. Anyway, he was talking to me in this wonderful way, and moving his hands around as he does. And then we came to this side street. And as we crossed the street, we had to stop the conversation to make sure the traffic wasn't coming. And then when we got to the other side, the conversation started up again. And then he went off, and I went to my office. And I thought, I've got this strange feeling of elation. Why do I feel happy about something? Well, I don't know what. I thought, could something I had for breakfast? My walk through the woods? No, on the bus? No, not that, no. And then it came to me that when we were crossing the street, this idea had come to me. And this idea evidently was the idea of what I call a trapped surface. So I wanted a characterization of a collapse which had gone too far, and you couldn't get away from it. I had some idea of general kinds of arguments that one might use. And this trapped surface was something where locally, if you could imagine a flash of light all over the surface, then the light rays would be converging on both sides. That's the curious characterization. You normally think if you have a sphere or something like that, if there was a flash of light over that sphere, then the concave side, the flash would go inwards, the convex side, it would go outwards. But on the trapped surface, it's sort of both ways, it goes inwards. I knew that using the kinds of arguments that I developed in other contexts, that you would get some problems. And that this means, as I developed, I went to my office and quite rapidly sketched out an argument to show that you would get problem. Now, what I mean by a problem, you see, at the time, people were looking at solutions of Einstein's equations by evolving them from an initial state. So you have an initial surface, which would sort of one time means a space-like three-dimensional surface. It's a three-space. But, I mean, time doesn't have to be time in any sense of normal clocks. It just means it's like a one moment, a space-like surface. And your data on that surface would be enough to evolve and see what the thing did later. So that's the usual way people would think of the evolution of a system in general relativity or in physics. Normally that's the way you do it. You look at what happens in your initial state, you evolve the equations, and you see what the thing does into the future. So I was thinking in terms of starting from an initial surface. Also, I would say it's what's called non-compact, because I was thinking of a universe which is spatially infinite. Really, it could be a local argument. It doesn't really matter whether it's spatially infinite or not, because I'm only looking at something fairly localized, so whether it closes up or not in the large is not really very relevant. But the initial surface could sort of go out to infinity. And if you have a trapped surface, and if you have a condition on the matter, so this tells you something about the curvature, which the focusing of the light rays is necessarily positive. It means that the local energy flux across the light rays is non-negative. And that's normal physics would say that. The dust of Oppenheimer-Snyder solution would have that. Any realistic solution of collapsing material, you would have this non-negative energy flux across the light rays. And I realized that you would have trouble if you look at the future of this initial trapped surface. When I say the future, that means all the points that can be arrived at with curves which go into the future. So that means they're what are called time-like. They, within the local light cone, they don't exceed the speed of light. What is that region which can be obtained into the future from that trapped surface? And if you look at the boundary, I knew various theorems about boundaries of futures, and the fact that every point on that had to lie in a light ray, and if you follow that light ray back into the past, then either it would go off to infinity, which is not the situation we're looking at here, but it would end up on the surface which you're looking at the future of. In this case, it's the trapped surface, so it ends up on the trapped surface. But on the trapped surface, you've got the light rays focusing, and once they start focusing inwards, there's nothing to stop them focusing inwards if the energy flux across the light rays is non-negative. So from that you deduce that the boundary of this future is finite, or what's called compact, really. And I had a rather sloppy argument in the paper about showing that this compact boundary to the future of the trapped surface would lead you to an incompatibility with the initial Cauchy surface being non-compact. And so you have this finite boundary to this future, and you map it back onto this finite. I stupidly didn't use an argument that I knew when I described this argument to Charlie Misner, who was a contemporary of mine at Princeton, where I studied. That's where I learned a lot of physics. After learning a lot from Dennis, I learned a lot more when I was in Princeton. Charlie Misner was one there I got on pretty well with, and he said to me, "Why didn't you use a certain result?" which he'd mentioned to me before, and I knew perfectly well. I said, "My God, I should have used that result than the one I did use." It makes the argument much neater, much easier. So using Charlie Misner's component to the argument, you get a really very direct and simple argument to show that the starting off from this open, that is to say non-compact initial surface, to come to something which has this boundary, this trapped surface which has the boundary of the future is compact, you have a contradiction, so that you can't do it. So it means, now you see, is this what you call a singularity? In my paper, the title of the paper did mention the word singularity in the title. I don't think it's used anywhere else in the paper. And certainly when I looked at these things in more detail later, you could see there are various things could happen. It doesn't have to be a singularity in the sense of curvatures going to infinity, like in the Oppenheimer-Snyder collapse, but something problematic happens. And the sort of thing you could say is problematic is this Cauchy surface description doesn't work. You can't say the evolution of this initial data goes crazy, and you can't do it. And why it goes crazy might be for one reason or another. It doesn't necessarily mean that the singularities are of the nature of curvature going to infinity. In fact, I don't think I called them singularities in general. The term singularity was used much more broadly later on by Stephen Hawking. You see, I gave a talk at King's College, London, where I described this argument I had given, which is, I think, 1964, in December 1964, something like that. And I remember I was very pleased because John Singh, who was an Irish relativist, I was very pleased he was at my talk, because I liked his books very much, because they were all very geometrical, and I had a very geometrical way of thinking, and so I learned a lot from Singh's books. And so I gave the talk, and he was there. According to the movies, Stephen Hawking was at my talk, but that was quite wrong. Dennis Sharma heard about my talk, and he asked me to give a repeat at Cambridge. I gave a repeat at Cambridge. Stephen Hawking was present at that. I then had a sort of private talk afterwards with Stephen, with George Ellis, I think Brandon Carter for some of the time. Stephen picked up on these things very quickly and started to apply them to the cosmological singularity, the Big Bang singularity. And could you say the same sort of thing? And he ended up writing a thesis which, a big part of that thesis had to do with singularities in cosmology. Yes, Stephen's PhD thesis, it actually consisted of 4 topics, curiously enough. 4 topics, only one of which was on the singularity theorems in cosmology, what he'd done at that point. I remember writing in my report, I was one of the referees, I should say. I was a referee, Dennis Sharma was a referee, and according to the movie, Kip Thorne was a referee. That's complete false. He was not there. We only had two referees. And I remember I had come armed with a list of typos and various little errors, and I brought them up, and he's corrected all of them by the time we had there. But you see, there were 4 parts to his thesis. Only one part consisted of this singularity theorem stuff, which he developed much more later on. But I think in my report I said any 2 parts would be good enough for a PhD, any 2 of the 4. So it was certainly a very good piece of work. These were continuing the kinds of arguments that I'd used, the argument being that you could apply them not just to a local collapse, but this sort of cosmic collapse, that if you imagine that the Big Bang was the result of some kind of bounce, that there was a collapsing universe which bounced and came out again, and the argument that Stephen was groping for, he did have some good arguments, were that you still had to have singularities. And eventually we wrote a joint paper together, which encompassed several more than the arguments he'd already worked on. But that showed that you could apply it either to the local collapse of to a black hole, or to the singularities in the cosmology situation. In fact, the term singularity, I never used it initially, but Stephen insisted on using it for all these different problems. He says, let's call it a singularity, whether it's light rays getting trapped in some way or this or the other. Let's call that singular. And eventually I went along with his terminology. In the paper we wrote together, I adopted his terminology. I don't think I did prior to that. I don't think I did afterwards. I think all these things could be, well, I think I was more specific to it. They don't have to be curvature singularities. That was well understood.
Some people would say this shows the beginning of time at the Big Bang or the end of time if you were to travel into a black hole. Other people say, no, it's a signpost to new physics. You've shown the need for new physics, whether it's quantum gravity or something like that. What was your interpretation?
Well, I wouldn't really distinguish between those 2 views very much. I would say, okay, classical general relativity goes wrong at that singularities. And this was common belief now, you see. I should mention that the paper by Lifshitz and Kalatnikov, which had an error in it, after my paper came out, people began looking back at that paper, in particular Belinsky, who was another Russian, and I think it was Belinsky probably who found the error. But anyway, there was a paper for Lifshitz, Kalatnikov, and Belinsky, and the 3 of them wrote a paper correcting the error in the original paper, showing that in general you do get these absolutely wild curvature singularities. And that's probably correct. Now I think what they did with this correction is very likely the right answer. I don't think there's any general argument to show that what they do there is really a generic situation, but it's fairly convincing. And Charlie Misner, I mentioned Misner earlier, he also had an argument, very similar conclusions to the Belinsky, Lifshitz, Kalatnikov paper, showing the kind of singularities you get. So I like to call them BKLM singularities, which are extremely wild, and certainly curvature goes infinite. So the question you're asking me is, what does this mean physically? Well, I think it presumably means that you've got a quantum gravity situation, that you have quantum mechanics becoming important. Once the curvature, the Weyl curvature starts to diverge and you get curvature, radii of curvature, which are smaller than what's referred to as the Planck length. And the Planck length is a distance where you can't really go any smaller than that without quantum mechanics sort of spoiling the space-time. And I think that's a reasonable argument. It's sort of a bit hand-waving and a bit just playing with constants, but sure. It's a reasonable argument to show that if curvatures get that extreme, then a classical space-time is not a good description anymore. And so that you get something which has to have a quantum description, some sort of quantum gravity. Personally, I think that's not a very fruitful line to pursue. Perhaps I should put that differently. Maybe it is, and maybe one could have a theory which accommodates the singularities and tells you what happens after, in some sense, what after means. You don't even know what after means. If your time has gone all crazy, you see, the space-time is crazy. What do you mean by afterwards? But then Sure, there should be some kind of quantum space-time description. But it's not really much use to you because these things would only be inside black holes, and you wouldn't see any evidence for them. So you can't do much with your theory except have a theory which you might unifies things in a nice way. To my view, the right thing is the other way around. Quantum mechanics is in need of some help because of this crazy way in which the wave function collapses. It doesn't actually, the physics of the universe does not evolve according to standard quantum theory, the Schrödinger equation, if you like. It doesn't evolve that way. As Schrödinger was absolutely clear on himself when he describes his crazy Schrödinger's cat. He was trying to show, look, this is the implication of my theory. This daft kind of idea of a cat which is dead and alive at the same time. He's really saying, I don't believe that. There's got to be some better theory, which tells you what goes on. I think he's right. It has to be a better theory. And that's where to look for new theories of physics, where gravity, in my belief, comes in and fixes quantum mechanics for you, if you like. Rather than quantum mechanics fixing general relativity, which maybe it does in the singularities and black holes. But on the other hand, quantum mechanics needs a bit of fixing too.